Welcome back. In this video we are going to discuss solutions and the methodologies for solving certain type of KVPY questions, and we are going to discuss questions from first year organic part. So let us look at. Yes, here is the first question. How is A related to B? So here is A, and the functional groups are ester here and nitro. And if you look at this, there is one hydrogen which is not seen, but you have to notice it. And this is also ester, and this is nitro. So let us look at the options available here. Structural isomers. Are they structural isomers? Yes, they are, because functional groups are the same. And the difference between these two is only, the parent chain. Their molecular formula must be same. So it's a structural isomer, it's true. Then functional group isomers. Are they functional group isomers? For having functional group isomerism, you need to have two different functional groups. If you look at this, there may be argument that this is a aldehyde also, sir. So it cannot be ester alone. But please know that when you name it according to IUPAC rules, we are going to name it as a formate only, because ester is a principal functional group. So if this is formate, that's ester then. So here it is ethanoate. So this is also ester. So functional group is same. So it cannot be a functional group isomer. Then, are they metamers? Yes, they are metamers, because here you see it is hydrogen and here it is methyl group. So they both differ in the alkyl chain attached to the either side of the functional group. So that means it is a metamer. So they are metamers. Are they optical isomers? So let us look at the carbons here. So there is only one sp3 carbon here, which is obviously not a chiral molecule, chiral carbon, and this is also not a chiral carbon. So that means it's very simple. They are not optically active. They both are not optical isomers. So here also it's not chiral carbon. Position isomers. Are they position isomers? So for having position isomer, you need to have a same parent chain and different location of the functional group or multiple bond or something like that. So here we don't have that. So it is actually only first statement and third statement are correct. So they both are related as structural isomers and metamers. So it's option C. So let us move on to next question. Yes. So try solving it. Pause the video and try solving it. Yes. Now let us look at the answer. Correct structure of ethyl, 3-ethyl, 4-methyl hexanoate. So first let us look at the word root, hex, and functional group, ester. So here all are esters only. So in naming esters, the first group which we write is going to address the alkyl group attached to the oxygen. So this molecule is ruled out because it is methyl here. So all others are still to be analyzed because all are ethyl. Now next is hexane. For hexane, you need 6 carbon atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So all are 6 numbered chain. So we don't have any other way to check the word root. So let us look at the substituents now. 3 ethyl. So 1 is here. First carbon is carbonyl carbon. 2, 3. 3 ethyl. So this is ruled out. This cannot be. Then 1, 2, 3. This is also ruled out. That's all. So 3 ethyl, 4 methyl. So it's option D. So fourth option is the correct answer. Next. Number of sp2 atoms in the following molecule is. So you can pause video and solve and check yourself. This is a great opportunity so that you can practice well in advance. Number of sp2 atoms in the following molecule. So let us mark now all the sp2 atoms. So all the carbon atoms of benzene are sp2. 1, 2, 3, 4, 5, 6. Then there is this carbon 7. This oxygen, which is also sp2, 8. Even this oxygen is actually sp2 in order to participate in resonance. This is very important because if that is not sp2 hybrid, then the lone pairs cannot participate in resonance. That's a very interesting part here. So it's total 9 sp2 atoms. So it's option A. Let us move on to next question. That is fourth question. Yes. The incorrect statement regarding the following molecule is. So here is the molecule. It's a amino acid. So yes, it seems this is a sp2 atom and this is a chiral carbon because all the 4 groups attached are different. There is a hydrogen here. You should notice that there is hydrogen. So yes, it is a polyfunctional molecule showing stereoisomerism. Yes, it is true. It does not show optical activity due to plane of symmetry, hence absence of chirality. Oh, this is not a correct statement because it has a chiral carbon. If there is only one chiral carbon, then the molecule is optically active. Molecule is optically active. Very important point. Next. It contains chiral carbon and has R configuration. And here there is both B and C. So we have to look for this. If it is R, then this will not be the answer. If it is not R, then this will also be wrong. Then option D will be the answer. So we have to check for the configuration here. So let us look at this way. We have to assign priority rules here. So very simple. You can convert this to Fisher projection and find out also, and you can directly assign the priority and find out also. This is nitrogen, so priority 1 here. Then you have carbon attached to oxygen here, carbon attached to carbon, so it is 2 and this is 3. So if you look at this counterclockwise and the hydrogen is behind. That means it is going to be S configuration. So because it is S configuration, this option also is wrong. So this is the incorrect statement. So the incorrect statement regarding the following molecule is both B and C are incorrect. So it's option D is the answer. Next, which of the following lack a pair of electrons? Yes, again, very important conceptual question. So how to identify a molecule lacks a pair of electrons or not is to find unsaturation. Not only unsaturation, lack of octet essentially. So here all atoms are having octet. Here you see there is a positive charge. What is the meaning of positive charge? Positive charge means it has only 6 electrons here and it is sp2 hybrid. So this lacks electron. So this is a molecule which lacks a pair of electrons. Then here all have octet. Oh, see, there is a boron here. Boron will not have anyway octet. So it has a vacant orbital. This also has 6 valence electrons essentially. So that's how this is also lacking a pair of electrons. And here there is no lack of electron. So it's B and C. Both B and C is the answer. They both lack pair of electrons. So fifth one is option B and second option. So let us move on to next question. Yes, you can pause the video and solve also. The correct order of enthalpy of hydrogenation for the following molecule is, okay, so we all know that stability is inversely proportional to enthalpy of hydrogenation as well as combustion actually. But here they are unsaturated compounds, so we have enthalpy of hydrogenation. Now let us first understand the order of stability, then we can surely find out order of hydrogen, the enthalpy of hydrogenation. Of all this, if you see, this is having the lowest number of alpha hydrogen, that is only 2. So as a consequence, what you can expect is it has lowest stability. Now next, remaining 3 have 6 alpha hydrogens, all have 6 alpha hydrogens, and now the stability, we know that para isomer has more stability than cis isomer because it has symmetry and less steric hindrance. But you look at this R has exceptional properties in exhibiting stability. So here what exactly happens is that the hyperconjugation structure which is there has a primary carbanion. This is a primary carbanion. This is a CH3. Whereas if you look at the trans isomer here, the most stable isomer among the other two is a trans isomer. This one, when it exhibits hyperconjugation, the structure becomes CH2, C, C minus, CH3, H plus. So this is a secondary carbanion, whereas this is primary carbanion. So here number of hyperconjugations are same in all 3. Now there is a comparison between steric hindrance and stability of hyperconjugation structures. Now of all the hyperconjugation structures, this molecule has primary carbanion in all hyperconjugation structures, which is more stable compared to secondary carbanion, which is the case for the other two. So as a consequence, stability order, when you see, it is R, which is most stable among all. So then it is P, then it is Q, and then last is S. So this is stability. If this is stability order, opposite will be order of enthalpy of hydrogenation. So highest energy will be liberated by S, then Q, then P, and minimum will be R because it is most stable. So it is option B which is the correct answer here. It was very conceptual and very deep question. Let us move on to next question. Correct statement about the following molecules is. So these are conjugated molecules. Let us see the statement. C double bond C bond order is identical in both structures and so is the bond dissociation energy. This is the first statement. Structure 1 has higher CC bond dissociation energy than that in case of structure 2. Structure 2 has higher CC bond dissociation energy than that in case of structure 1. Only structure 1 has resonance possible. This is wrong anyway. Both have resonance possibility. Let us write resonance structure. Then it will be more easy and convenient. So resonance structure, if you see, this is O, and resonance structure will be like this, O minus plus. So there is only two resonance structures here like this. Hence, I mean the ones which contribute more. So obviously, the bond order, if you see, is almost like 1.5. Now coming back to the second structure. Second structure, if we see, the resonance structures are like this. And next to it has a lone pair to be noted, double bond O. So you have two-way resonance here. It is not very helpful, very important. It's not always helpful. Suppose this bond moves here, it moves here. So there is double bond here and NH2. Now there is also possibility that this lone pair moves here and oxygen moves there. So it will be something like this. O minus double bond NH2 plus. So basically here it will be plus here. Basically here the resonance is of two-way type. So there is no proper resonance when we look at this particular carbon-carbon double bond. So here if you see, bond order will be slightly higher than this. Out of three resonance structure, two of them have double bond only. So it's like having more bond order. That means CC bond will be stronger here compared to CC bond in case of this. So as a consequence, CC bond in this second structure will be stronger. So second structure has higher CC bond dissociation energy than in case of structure 1. So it's option C which is going to be correct answer. Let us move on to next question. Yes. Correct order of acidic strength of the substituted phenols given below is. So here are three phenols which are substituted with NO2 at different positions. So first let us look at A. So phenol is there, one ortho group is there. Ortho nitrophenol will have a hydrogen bonding, or you can say ortho effect, and here all the NO2 groups are at meta, so it's only minus I. Here minus I, and this will also offer minus R, so that you should know. Here both will offer minus I. Here this will offer minus I, predominantly minus R and minus I. This will offer minus I. So if you look at option, the structure A, B and C, B will be expected to show least acidic strength. We'll look at that now. Maximum will be one of C or A, because in both cases there is resonance, negative resonance of NO2. But because of ortho effect, we know the acidic strength of phenols is reduced because there is an intramolecular H bonding here which reduces the tendency of ionization. That means this hydrogen does not prefer ionization because of the stabilization due to hydrogen bonding. So as a consequence, most acidic will be C, and least is B because there is no resonance, no minus R. So as a consequence, most acidic will be C, then it is A, then it is B. So if you look at the answers, it should be option C. Let us move on to next question. Yes. Which set of reagents will bring about following conversion? Yes. Let us check each of them. Concentrated sulfuric acid and dilute sulfuric acid. So when we add concentrated sulfuric acid, it will perform elimination. So this will eliminate, and it will form a most stable alkene. Then on hydrolysis, we get back the same result, because here electrophilic addition with rearrangement, so carbocation is involved. That means you will get same tertiary carbocation, and then you will get OH. If you want me to write, let me show it. OH, H plus. So basically it will form carbocation like this, and this will undergo elimination to form this one. This on hydrolysis, acid hydrolysis it is. It will form most stable carbocation, again same carbocation, and it will form OH here. So this is not the method. Second, dilute H2SO4. Again, dilute H2SO4 means it will undergo protonation. Then there is no heat also, so it will remain same compound actually, no change. Hg to mercuric acetate. So all this is a waste actually. There is no use of this second reagents at all. Third one, P2O5 heat. Yes, P2O5 heat will perform elimination. So you get this product only, P2O5. So I will fast forward the process. So you get same elimination. So once you get this alkene, then there is B2H6 THF and peroxide in alkaline medium. Yes, this will actually perform hydroxylation. It's a hydroboration oxidation process, and it will give a product which is going to be like this, and that's our product which is expected. So option C has to be the answer. Third option is the correct answer. And here soda lime is there. It's again not useful. There is no carboxylic group here. Let us move on to next question. Yes, and this is our last question for this series. Which of the following are expected products? Okay, So here there is a NBS, and we should know NBS is N-bromosuccinamide. It's like this. This is N-bromosuccinamide. There is NHBr. So if it is NHBr, then it will be salt. It should not be salt. It should be normal compound. So it is directly attached to Br. That's the speciality. Okay. So it is directly attached to Br. So it will basically give Br free radical in terms of sunlight. Okay. Low concentration of Br free radical is obtained by this reagent. Now you have alkene, cyclic alkene. So this will also interact with Br free radical and form a radical only. So let us form free radical here. So now allylic positions are to be activated because that's how the reaction will take place. This is one allylic position, this is one allylic position, and this is one allylic position. All three allylic positions can give rise to one type of free radical, and it is possible. So please note this, it is possible to have three types of free radicals. So one is this way, another one is this way, and third type is very stable one here and this way. And all are different free radicals. So please make note of this and be careful when you draw free radical. So next if we see this, this can actually rearrange itself. I mean, it has a possibility to resonate and form if this bond shifts here, and this will be the free radical, and here it's going to be identical. Whether this bond shifts there or not, this is going to be identical. Now here also there is a possibility of resonance. If this bond shifts here, it will form something like this. Double bond outside and free radical here. So this on bromination will form double bond here, and there is Br, and this on bromination form double bond here, Br here. Even if double bond shifts here and Br comes here, IUPAC name will remain same for this. That's why I am not making any arrangement. I mean, I am not writing a resonance structure here. However, here you get two possible products. So this is the first product which I have written. The second product. Here this can also directly combine with the free radical and form this type of compound. There is no hard and fast rule that it should only resonate first and then combine. So there can be Br. So this is third product. Even this free radical can directly combine actually and form something like this Br here. This is fourth product we have, and this one again Br can react and form double bond here and Br here. This is fifth product. So these are the possible products which we can expect. Now if we compare, there are very less number of, it's easy to compare now. If you see D, this is D, this is D. And if you see C, C is here, this is C. Okay, this is C. B, if you look at B, this one matches with B. And here 1 matches with A. So all these possibilities are there. So it is option 4, all A, B, C, D. So that's how free radical reactions can give rise to varieties of products. Now if for the sake of discussion, we can say out of this which is most stable, or you can ask which will be the major product. So that is a very interesting question. The major product is expected to be we have most stable radical here. This is one most stable radical. Then we have stable radical here as well. Here as well. So basically one of these three will be a major. And yes, that's it for this video. Let us meet in next set of questions. So stay tuned. Thank you.